This is a second tutorial on pipe data input. In the first tutorial, we described the pipes using 7 ranges, 7 types, and entered the pipe OD and ID for the pipes. In this second tutorial, we will now review the rest of the pipe data form. The roughness. This is the pipe roughness, and it's used to compute the friction factor for the multi-phase flow correlations. Perforation fraction. This is the fraction of 7 length open to flow. The flow connection will be prorated based on the 7 length. For the outermost pipe, pipe 1, the flow connection is between this pipe and outer reservoir cell. For an inner pipe, pipe 2 or pipe 3, it will be the flow connection to the outer pipe, in this case pipe 1 for pipes 2 and pipe 3. For pipe 3, it will be a connection to 2 for this segment and to 1 for this segment range. Set to 0 if there's no flow connection. For an outer pipe 1, the flow connection is calculated using the Pisman formula for the productivity index. The flow connection will be prorated using this perforation fraction. For an inner pipe flowing to an outer pipe through a perforated segment, a default high transmissibility value is used to calculate the flow between the inner and outer pipe. The perforation fraction is used to multiply the default transmissibility value. By adjusting this fraction, the pressure drop of flow between the inner and outer pipes can be increased or decreased. Once the required flow rate has been achieved, then if the flow is through holes in the pipe wall, using the ICD choke sighting module, the number of holes and the hole diameter can be calculated. Alternatively, an ICD number can be assigned to the segment, and the ICD number of holes and diameter can be specified in the ICD specification form. This is the overall heat transfer coefficient, UO. Is defined at the outer diameter of the pipe. This is used to calculate heat flow for the current segment between the inner pipe and outer pipe, or between the outer pipe and reservoir. Heat flow Q is computed based on the overall heat transfer coefficient U, the A for the area of heat transfer computed at the outer diameter of the pipe for the current segment length. dt is the temperature difference between the inner and outer segment. The overall heat transfer coefficient should include all film heat resistances, scaling, insulation, pipe, concrete, which exists at that segment range, at this segment range, whatever it is. You can use the heat transfer calculation button here to calculate the appropriate value for the specific conditions for each segment range. Correlation. Currently this defaults to Baxter Bill, and it is the only correlation that is being used. Initial pressure. The pressure that's used to initialize the pipe segments for this current segment range. If the pressure is not entered, or has a value of 0, then the initial conditions of the segments, the pressure, the temperature, the oil, water, gas saturations, compositions, will be automatically set based on reservoir fluid conditions or based on injection conditions with this injection point in the tube. These columns will be ignored. However, if pressure is entered, then you must enter these columns as well. You only enter these columns of data if the pipe segments are blocked and no flow occurs in the specified pipe range, this range of cells here. The diameter of solid pipe. This is used to account for instrumentation tubing or similar no-flow tubes that occupy flow area in the current pipe. Effective flow area is reduced by the diameter of solid pipe. Grid dx and dy, reservoir permeability, reservoir skin, mechanical skin, all these are used to compute the productivity index for an outer pipe. For inner pipe, we don't have those columns. So for an outer pipe, a reservoir cell of that dimension or the same length as the pipe segment is assumed, and the Pisman flow formula is used to compute the Pisman PI using the size of the cell, the permeability of the cell, and any skin that exists in the boundary between the segment and the reservoir. ICD number. This is optional. If we try to use a positive perforation fraction for a flow between an inner pipe and outer pipe, we can afterwards, using the overall heat transfer coefficient, using the ICD choke sizing button, we can use this option to size the ICDs required to produce that particular flow rate. So this ICD number is optional and is used to compute the number of holes and hole diameter necessary to achieve the target rate from an inner pipe to an outer pipe. Initial conditions from files. Even if we specify pressures and saturations in the segments for initial conditions, we can override them by reading initial conditions from a file. For example, if we browse, we can select a previous results file, and we can use that file, the conditions calculated in this file for this similar pipe as initialization condition. If we wish to do that for all the pipes in this case, and assuming that this previously run case has the same number of pipes, we can use the option for all pipes, browse, and then this will assign the same file name, same results file to all the tubings in this current case. And if we did this, then when we run the case, we will be using the results of the previous run as initialization conditions rather than specified initialization conditions here. This is the end of tutorial 2.